Hello and welcome again. So in this one, we're going to be talking about operators and elementary operations. Arithmetic functions include operators for simple operations like simple addition and multiplication, as well as functions for common calculations like summing or modulo operations and so forth. So in case I go and say A is 1 and B is 2, and I just add A to B, it's 3. This also works with matrices, so given two compatible matrices to add up as such, they're both a 3-sized row vector, so we can add them up as such. So 1 will be added to 3, 4, 2 will be added to 10, 12, and 3 will be added to 20, 23. You cannot add a column with a row. You can add two columns of compatible dimensions. You can also add matrices, so let's say I have a 2 by 3 matrix. 1, 2, 3, 4, 5, 6. This is my matrix A, and my matrix B is 10, 20, 30, 40, 50, and 60. Adding them will produce element-wise addition. So 1 plus 10 is 11, 2 plus 20 is 22, and so forth. There's many other operations you can do with matrices, such as you can multiply two matrices, the usual multiplication that we know about matrices. So what we just discussed is matrix addition. That being said, if we have something like A plus B and we're looking at its ijth entry, right? So ith row and jth column, then it would be aij plus bij. If I have something like this, 1, 2, 3, 4, and I'm adding it with 10, 20, 30, 40, the output will be simply just looking at let's say, the second row, first column. I'll add it with the corresponding entry in the second matrix, and I'll have 33 in the same position. That's what this means. However, matrix multiplication is a bit different. So A times B or AB, if I take a look at its ijth entry, it would be the sum over aik bkj. If I have the same matrix right here, but this time I want to multiply them together. Let's say I want to produce the first row, first column right here, right? What I could do is grab the from the second matrix and then do an inner product, which means a scalar product between two vectors. So that means that 1 times 10 plus 2 times 30. That's 10 plus 60, which is 7, right? To do this for the second entry in the first row, we grab the first row from the first matrix and the second column from the second matrix. So if I'm interested in this entry, as you can see, the output, the produced matrix, the row is generated by the left matrix, whereas the column depends on the right matrix. So if you want to move in rows in the output, you should vary the rows in the first matrix. Whereas if you want to transition between columns, you should do so in the second matrix. So this time we're going to inner product 1, 2 with 20, 40. So 1 times 20 is 20 plus 2 times 40 is 80. That's 100. Same thing, now 3, 4 with 10, 30. That is 3 times 10, that's 30 plus 4 times 30 is 120. Last but not least, we'll grab 3, 4 and inner product it with 20, 40. That's 3 times 20 plus 4 times 40, which is 60 plus 160, which is 220. Let's check our answer on Matlab. Generate the two matrices, 1, 2, 3, 4, and 10, 20, 30, 40, right? Now multiply them as such using the traditional asterisk. You're going to get 70, 100, and 150 to 20. Now if if you have only two numbers, 1 and 2, A times B is your traditional multiplication, so it's 2. Actually, if you do this definition of multiplication to numbers, you're going to see that you boil down to the normal multiplication, because n will be 1 and ij will only take one value, which is 1. So all this would be only A times B. So that's addition and multiplication. Subtraction is similar to addition. All you have to do is replace plus with a minus as such, minus right here, and that's it. So this guy would be 3 minus 30, which is minus 27. Let's do this. So A minus B. Oh, we did a mistake here. It should be as such. So that is 2 by 2. So now A minus B is the following. So minus 9 comes from 1 minus 10. Minus 18 comes from 2 minus 20. Minus 27, as we saw here, comes from 3 minus 30. Minus 36 comes from 4 minus 40. So that's matrix subtraction. And in case you're wondering, is there any matrix division? Well, yes, but it's not as trivial as you think. It's actually, once you see a matrix division, if it's not pointwise division or element-wise division, right, it's going to be something as such. So division is the inverse of multiplication, is the inverse operation. So let's write down multiplication. AB is equal to C. So one might think, oh, so I can do something like this. B is equal to C over A. Well, with some conditions, you could. And normally, this A is not denoted as such. People usually denote it as such. B is equal to the inverse of C times A. Because this is a left inverse. You can also have a right inverse or a right division. That is A times C minus 1. And they're not the same. So yeah, usually people use the inverse. Now, what does that mean? It means you're solving a system. So usually AX is equal to C. Matrix division is the equivalent of solving for X given A and C. So I know A, I know C. What is X? It is, if A is invertible, then it is A inverse times C. As simple as that. And the reason I say invertible is because you cannot invert a non-square matrix. A rectangular matrix is not invertible. It has something equivalent or close called a pseudo-inverse. I'm not going to talk about here. I'm going to create another linear algebra course and we'll tackle those in more details. For the moment, matrix division, let's say I have this matrix over here and X, I don't know. Let's define our C right now. So C is something like, I don't care. Let's put something like this. So this is my A and my C. X would be the inverse of A times C. This is my X. So if I go ahead and say A times X, I should be able to get C, right? You can also generate this using A to the power minus 1 as such. It's equivalent. So AX again is C. And yeah, that's basically it. Now you have the other pointwise. The pointwise operators are easy to understand. They're just, as the name suggests, pointwise. So let's say I have those two matrices, 3, 4, and 10, 20, 30, 40. And I say, oh, let me pointwise multiply both matrices. So in Matlab, it's a dot asterisk. So a dot before an asterisk means pointwise or element-wise multiplication. So right here, I don't need to grab any row, any column. I'll say, you know what? I'm too lazy. I'll just grab the first element from this matrix and multiply it with the first element here. As simple as that. So 10, 2 with 20 is 40, 3 with 30 is 90, and 4 with 40 is 160. This is also called the Shor-Hadamard product. So yeah, this is element-wise multiplication. You also have element-wise exponentiation. So in case I come and say A dot to the power B, it's just taking 1 to the power 10, 2 to the power 20, 3 to the power 30, and 4 to the power 40. We've also got element-wise or right array division. A dot divided by B, it would be something like 1 over 10, 2 over 20, 3 over 30, and 4 over 40. It's 1 over 10, 1 over 10. Now this is a right division, right? You also have a left division. You can do B dot divided by A or A dot left divide B. Note that this is the right division. This is the left division. So in that case, you'll have 10 over 1, 20 over 2, 30 over 3, and 40 over 4, which is a matrix of all tens as such. Let's give it a shot here. Going back to what we had, A is, and B is this. So A dot times B, as you can see, 1 times 10, 2 times 20, as we did here. 10, 40, 90, 160. Let's do the exponentiation, which I'm sure Matlab is not, yeah, it's so large. Those numbers are already really large, so you're not going to see the first element. In case you want to see it, do something like this, right? And look at the first entry. it's 1, right? 1 to the power 10 is 1. Let's do right array division as such, the 1 over 10s, and let's do this. Left division, it's all 10s, which is the equivalent of this. Right, so now we're going to talk about operator precedence. Even though this might sound trivial, it's worth noting that Matlab has its precedence rules, let's put it that way, for operators. So there's some operators that have a higher priority than others. I'm going to write them down here. So in case you have a big expression, I don't know what, that has parentheses, and you have got a plus b times another matrix to the power another matrix, the question is, which one is executed first? So the highest priority, we're going to write them down from highest priority to lowest priority. So 1 is parentheses. This guy has the highest priority. So in case you come and tell me, oh, I've got those 2 parentheses here, Matlab is going to execute this and this first. The second priority is matrix transposition. So dot dash, which is a transpose. You've got the matrix power, or the pointwise exponentiation. You've got the complex conjugate transpose, so also I'm going to write here complex transposition. You've also got matrix exponentiation, so this one is pointwise. You've also got the power as such, matrix exponentiation. 3, you've got the logical negation. Even though we didn't talk about it, it comes third. So logical negation, you've got the unity addition, unity subtraction, and everything that is unity. 4 comes plus the minus and the logical negation. 5, you've got element-wise or point-wise multiplication. You've got right division, left division, matrix multiplication. Those are pointwise, also the non-pointwise, so the traditional matrix division, left or right. Well, and by the way, the inverse that we talked about can also be done using division sign. We didn't show it, but it is doable. 6 is addition and subtraction again. 7 is the colon operator, so the colon operator is, if you remember, 1, colon 3 produces a vector counting from 1 to 3. This is the colon operator. 8, you've got the conditionals, so statements returning true or false, or 0 or 1 in Matlab. So less than or equal, greater than or equal, is equal or is not equal. So far so good. 9, you've got element-wise and, so also a statement returning true or false. Element-wise or comes 10, and you've got the short circuit and the short circuit or. Now for safety, if you want something to execute first, just use this guy right here. To control which statements you want to execute first, use parentheses. In case you don't have this chart in mind, you're safe to control your statements with the parentheses, okay? Let's see an example on this. Let's say I've got A, which is 1, 2, 3, and B, which is 4, 5, and 6. And I'm going to do something like this, right division with B, pointwise power 2. This will produce the following, whereas, and I'll insert some parentheses over here. We're going to see something different. This is 0.16, this is 0.08. And the reason is because in this chart, the power is priority 2, whereas the division is priority 5. So this guy is going to execute before this. To make sure of this, if I remove those parentheses and insert them here, I should be able to see this, right? So enter. There you have it. It's the same as without inserting any parentheses, right? That's all I have to say about operator precedence. So now let's talk about relational operations, which are basically operators done with the purpose of comparing two quantities. Let's start off with the equality. So say I've got A is 2 and B is 3. It's double equals. That stands for a relational equality. So we're testing if A is equal to B. Obviously they're not equal, so I'll get a 0. In case they are, so A is equal to 2, we get a 1. So A is 10, B is 10 as well, you get a 1. You can do so using the EQ method. Are A and B equal? Yes. Is A equal to B plus 1? It's not. So there you go. You can also test for equality of characters. So A and A are equal, but A and B are not equal. There's also the greater than or equal. So if A is 5 and B is 3, is A greater than or equal to B? It is. Is A less than or equal to B? It is not. This could also be done using the greater than or equal method, GE, or the less than or equal, LE. Now if you want strict inequality, all you have to do is do this without the equal. So for this, in case you want the equivalent method, it will be not greater than or equal, it will be greater than. So GT. Is A greater than B strict inequality? Yes. Is it less than B? No, it's not. Now, in case you want to test for not equal, you can do something like this. Tilde sign, it is not equal to B. Or you can use the NE, not equal. So now you can also determine array equality. So let's say I've got 1, 2, 3, and B is 1, 2, 4, let's say. In case you do this, it's going to test element-wise equality. But in case you do this, it will test for all the array. So you should have all the array exactly the same. The exact copy. If it is equal, this time I can get a 1. You can also do this using this. So test for A is equal to B element-wise, and if they're all 1s, return a 1, else return a 0. You can do so using the product of A equal to B. So if 1 is 0, this will be 0, right? So say again A 1, 2, 3, but B is 1, 2, and 4. Now, is A equal to B? The last one is a 0. So if I do a product, we'll see a 0. Also, you can test for multiple arrays. So let's say I've got a C, which is 1, 2, 3. A is 1, 2, 3, B is 1, 2, 4, and C is 1, 2, 3. All I have to do is say is equal A, B, C. It's obviously 0 because B, last element of B is not 3. If I change it, this should return a 1, right? We've also got a slightly different method, which is equal N as such. This guy ignores or treats the NaN as values that are equal. It's as if we're ignoring NaNs. So let's talk a bit about logical operations. So logical operations return true or false when we're evaluating certain conditions. We know that logical data type represents true or false states using 0 and 1. As we saw, is A equal to B? All we see is 1s and 0s, indicating true or false. Now, there's some certain Matlab functions that return logical values to indicate fulfillment of a condition. In case it's true, you will see a 1. In case it's false, you will get a 0. You can use those values to index another array or to execute a certain block of code or to trigger a certain function. It depends on what you're doing. So let's start with the logical AND, right? So let's say A is 1 and B is 0. Actually, let's do something else. A is 0, 0, 1, 1, as you can see, and B is 0, 1, 0, 1. If I stack A next to B, you can get the truth table of 2 bits. So 0, 0, 0, 1, 1, 0, and 1, 1. Let's do a logical AND operation. So A and B. You should be able to see all zeros except the last entry, which is 1, because we know that the truth table 0 and anything is 0. So that being said, only 1 and 1 is 1. In case you do 6 and 5, you get a 1, because Matlab treats anything that is not 0 nor 1 as a 1. So 2 is a 1, 3 is a 1, 5 is a 1, 6 is a 1. So back to 1 and 1 is 1. 1 and 1 is 1. You've also got the OR. So back to A, B. A or B. 1 or anything is 1. If I take a look at A, B, A or B, there you have it. So 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. And 1 or 1 is 1. In contrast to the AND, which was all zeros except when they're both true. You can think about it in a more common sense. So if you want to think about AND, you require that both statements are true. Whereas the OR, at least one statement should be true, so that I say the compound statement is all true. You've also got the NOT. So if I want to look at not A, it only negates what I have. So a false becomes a true and a true becomes a false. Also generated using not A. Now you've also got the XOR, or exclusive OR. So exclusive OR is, so as you can see, the XOR returns true only when the number of true inputs is odd. As you can see here, it's true because there's only one true input. Here it's true because, again, only one true input. False here because we have no true inputs, 0, and two true inputs, 2, which is not odd, it's even. Let's see this with 3 inputs, so A in that case would be such, B would be, and C would be 0, 1. Stack them next to each other to see the truth table for 3 variables. Let us take a XOR of 3 variables. So I took the output of XOR A and B and XORed it again with C. So as you can see, we have ones only when the number of inputs, the number of true inputs is odd. So here there are 3, here it's 1, 1, and again 1. Zeros when we have an even number of ones, right? There you go. And you can also write this down using an algebraic expression in case you've taken discrete math, some course, or logical gates in electronic engineering. The following should be familiar. So a bar is not A, and the AND operation is denoted as such, as plus, or as such. The AND is simply a multiplication, or as such. Now, a XOR is usually denoted as such, a circle with a plus inside, and the algebraic expression that generates it using simple AND or OR gates is the following. So it's A plus B times not A plus not B. So you can verify that this expression actually generates the 4th column. Actually, this algebraic expression will return 1 in case A is 1 and B is 0, or A is 0 and B is 1. So we only return true only if one input is true, else false, or the number of true inputs is even. Now we've got a function called all, like all. In case I say all A, it's 0, all B is 0, all C is 0. Why is that? Because they contain at least one 0 entry. So if I go ahead and say all A plus epsilon, it's a 1. Because now we have no 0 entry. Seeing it clearer, all 1, 1 is 1. 2 is 1, 1, 0 will be 0, okay? Now next off we've got the any, which returns true. So any, let's say my A looks like this. Any will return true if any of the elements of A is non-zero. So it looks for one non-zero. If it finds a non-zero element, it returns true. So any A is true, B looks like this, and C looks like this. So we have at least one non-zero element. So all of them are true. It will only return false if I have a 0, if I have all zeros as such. And you've got the find function. So let's say I've got this vector, and I'd like to find the entries of, or the indices of entries that correspond to a certain condition or fulfill a certain condition. So I'd like to find, in other words, I'd like to find the row and column indices of, for example, entries that are equal to 30. R would be 1 and C would be 3. Let's extend A for another 30 and see what happens with multiple fulfillments. So R would be 1, 1 and C would be 3 and 5, right? You can do this, or C. You're just returning the values of elements that are equal to 30, which is 30. Now let's say you want to have some relational operation as such. All elements that are greater than or equal to 30 are sitting right here, right? So R would be 1, 1, 1, and C would be 3, 4, 5, right? Also check for non-equality, so not equal to 30, not equal as such. 1, 2, 4, so elements sitting at 1, 2, and 4 are not equal to 30. So that's all I have to say about logical operations. Let's move forward to bitwise operations. Okay, now so if you're working with bits and you would like to do operations on a bit level, there's some cool Matlab functions for that. So let's start off with the bit AND. And what bit AND does is it simply performs the AND operation per bit. So bits are either 0 or 1, right? 0, 1, 0, 0, 1, 0, 0, 0, And if I want to do a bit and, which is a multiplication, all I have to do is grab bits on the same level and just multiply them with each other. So 0 by 0 is 0, 0, 1 times 0 is 0, and 0 times 1 is 0. It's all zeros. How can you do this on Matlab? It's as simple as using a function called bit and. So let's say bit and, I don't know, 6 and 2. I'm going to get an error or not. But let's specify the format of 6 and 2. It's 2. So this is by default. The default thing is int 8 or uint 8. I'm not sure. But for safety, just find the type of the bits the numbers you're inputting. So what is 6 here and what is 2 here and why do I get a 2 here? So let's represent 6 and 2 as 8 bits. So 6 is represented as, 6 is 2 power 2 plus 2 power 1. That being said, if I want to represent it on an 8-bit level, it's 0, 0, 0, 0, then 0, 1, 1, 0, right? And the 2 is 2 power 1, so I perform a multiplication or a bitwise and 0 times 0 is 0, 1 times 1 is 1, and the rest is 0. You can verify. So the equivalent of this is again this, which is 2. That's why we see a 2 right here. Now let's say you're working with negative numbers, I don't know, minus 5 and 6 for example, you get 2 again. What just happened? Negative numbers are represented on Matlab using 2's complement. So minus 5 in 2's complement format will be represented as follows. So 5 is written as the traditional way. It's 2 to the power 2 plus 2 to the power 0. So 5, you would write it as such. And minus 5 is the 2's complement of this guy, which is obtained first by inverting each bit. So the 0 becomes a 1. And a 1 becomes a 0. Then you add 1. So as such, let's add 1 to this guy. We'll get 1, 1, 0. So this guy is the equivalent of minus 5. Now let's do a bitwise bit and of minus 5 with 6. So this is my minus 5 and my 6 would be right here. So I'll just copy this down here to a bitwise and. So 1 times 0 is 0, 1 times 1 is 1, 0 times 1 is 0, rest is 0. The equivalent of this guy is again 2, okay? You can also use a bitwise or, you get a minus 1. It's the same way, but you use an addition instead of multiplication, right? Now let's say I've got the 6 again, so 6 right here, let me just copy paste it here. It's getting messy up there. 0, 0, 0, 0, and 0, 1, 1, 0. Let's say you'd want to do a bit complement of 6. You'll get a minus 7. Let's invert all the bits. That's what the complement does. You'll get 1, 1, 1, 1, 1, 0, 0, and a 1. So this representation is inverted, but it does not correspond to minus 7. And the reason why is because it's in the 2's complement of minus 7. 2's complement of 7. How do we see that? We do the inverse operation of what we did here. That is invert, then add. Now we subtract, then invert, right? Subtract 1 from this guy, you'll get 1, 1, 1, 1, 1, 0, 0, 0. Then invert. You'll get a 0, 0, then 1, 1, 1. This is 2 power 0 plus 2 power 1 plus 2 power 2, which is 7. That's why we got a minus 7. You also got the bitwise XOR. You get a 4. You just do a XOR operation per bit. 6 and 2, again, 0, 0, 0, 0, 0, 1, 1, 0, and the 2 is an XOR. So remember, XOR returns 1 if only one of the inputs is true, else false. So this is false, this is false, this is true, this is false, and the rest is false. This is the equivalent of 2 power 2, which is 4. There you have it. So those are the most basic bitwise operations on Matlab. Last but not least, we're going to talk about set operations. So if you have sets, you'd like to do, I don't know, unions of two sets, intersections, set membership, and so forth. So let's start with the two basic set operations, which are intersection and union. So what are those? Let's say my A set and my B sets are like this, A and B. The intersection lies in the red part, whereas the union is the blue part. So intersection is the common part, and union is everything in the two sets. Let's see it on Matlab. So if A is 1, 1, 6, and B is 6, 6, 7. Intersect A with B will return 6 because 6 is the only common element between A and B. Whereas the union of both sets would be 1, 6, and 7. Note that there is no redundancy, which means that 1 will not be mentioned twice and 6 will not be mentioned 3 times. Now, in case you have, matrices, so 1, 2, 3, 4, 5, 6, and B is 1, 3, 4, and 5, 7. So union A with B would be 1, 2, 3, 4, 5, 6, 7 because it's treated as a big column vector, whereas the intersection is 1, 3, 4, 5. That's the common elements between A and B. 1, 3, 4, and 5. You've got unique. Unique B will return non-redundant elements. So 3 is mentioned twice. Unique B will return 1. 3 only once. 4, 5, 7. Let's see it as a vector. It's easier to visualize it that way. So unique A would be 1, 2, 3, 4, right? 2 mentioned once. You've also got the is sorted method of A. Returns true if the array is sorted, and false. So let's set the last element of A to -1. It's not sorted anymore. So is sorted? No, it's not. It goes up, then goes back down. You've got the isMember function. So let's say I have the array 5, 3, 4, 2, and B is 2, 4, 4, 4, 6, and 8. Let's run isMember AB. We'll see 0, 0, 1, 1. For each element of A, it checks if it is found in the vector B. So is 5 found in B? No, so 0. Is 3 found in B? No, so 0. Is 4 found in B? Yes. Found in the second, third, and fourth position, so 1. Suffices that it finds it once, as is the case for 2. So 2 is found once, so 1. You've got another slightly different function called isMemberTol. So with a certain tolerance, find if entries of A are found in B. So let's add a small number, 0.01, and check. So it's all zeros because members of A are slightly shifted by 0.01. So in case, you want to relax this finding method, you don't want a hard decision, let's put it that way, you can run isMemberTolerance and pass a certain tolerance. So let's say 0.02. Again, we found it with a certain margin of A. If I put 1, it works. 0.9 still works. 0.1 does not work. So there's a certain tolerance defined by the third parameter. Okay, now let's say you're working with tables and you'd like to join two tables or a union of tables. Let's say I have a table of the following information. So A, B, C, and D transpose 1, 2, 1, 2, and let me pass in the variable names, which are, var 1, this is my A, this is one table. I have another table, B, which contains the following information with variable names, this time var 2 and var 3. So A and B. Notice that both of them have something in common, which is var 2, right? So if I go ahead and say join A and B, see another table, which figures out that anything that corresponds to 1 in var 2 is an E, var 3, and 2 is an F in var 3. You can see A, B, C, D, 1, 2, 1, 2. If it's a 1, then var 3 should be E. If it's a 2, then var 3 should be F. It merges or joins them using the key variables. Okay? So that's about it. That's all I have to say in this lecture. We've seen how to perform a lot of Matlab operations, such as addition, subtraction, multiplication, division of numbers and matrices, pointwise operations as well, relational operations if you care about comparing two quantities, logical operations in case you're working with true or false conditions or Boolean expressions, set operations, we saw how to do union and intersection of sets, join two tables, check if an array is sorted or not, check if some members of one array are found in another, right? Find the unique elements of a certain array, And last but not least, we saw how to deal with bitwise operations. In the next one, we'll talk about more advanced stuff like loops and conditional states. I'll see you then.